Okay, so we're gonna be using the ideal gas law, PV equals nRT. So for 5.9, which variable are we solving for? Yeah, volume V. So we can rearrange this equation as V equals nRT divided by P, and then we just need to plug in our numbers. So we have 1 mole for N. Now for our R value, we know that STP is 1 ATM and 273 Kelvin. So if we have ATM, Kelvin, and moles as our units of measurement, that means we need to use a 0.821 value for our gas constant, okay? If you guys converted, I guess you can use a different R value, but that's extra work for you guys. And then for temperature, 273 Kelvin. Okay, and then you could divide that by 1 atmosphere. And then that'll give you a final volume of about 22.41 liters. If you guys are wondering why I did 273 instead of the 0.15, usually in your calculations, it won't make a big difference. So when you guys bring the problems, if you just want to do 273, that's totally fine as well. Okay. All right. Any questions? Chilling. Okay. So based on our calculations, I want you guys to take a look at the chart down here. And I want you guys to look at this table and see if you could figure out with the person next to you in the next 40 seconds, which one of these gases, and this is real life data, which gas is actually most similar to an ideal gas. Okay, so take about 30 seconds and then we'll go over the answer. All right, so which gas is most like an ideal gas? Yeah, he, whatever. Okay, it's gonna be helium. Now, another thing that we can think about other than this value right here, because depending on how you round, you might get a different value, right? Or something that's a little bit different. But if you guys remember an ideal gas, there are a couple properties of ideal gases that we need to think about. One of the assumptions is that the gas takes up no volume, right? Okay, so if you look at all of these compounds, the smallest one is helium because helium has a mass number of 4, right? It's much smaller than any of all these. So it fit the description more. The other one is that there is no interaction between the gases, and helium is inert, as you guys learned about noble gases. So by all metrics, helium is most similar to an ideal gas, okay? It's because helium has the smallest volume and it's inert. It doesn't react with anything. It's a loner, like me. No friends, yeah.
Do we end up using this like a substitution for ideal gas?
That's like operative, like chemistry classes, yeah. Yeah, you talk about ideal laws until like your senior year of college in physical chemistry. So you don't need to worry about that. Yeah, once you go to college, you start with regular chem, which is this, and then there's organic chemistry, quantitative analysis, there's biochemistry, physical chemistry, inorganic chemistry, a lot of chemistries. It's too much, man. Me, I liked organic the best because that's where you learn about how to make different compounds. And then I started looking at the formula for meth and I was like, oh. For the record, I will never make meth. I have never made meth. And I never will. I can, but I mean, I could do a lot of things that I'm not gonna do. But anyway, moving on. Yes. Yes, exactly. Thank you. Alrighty. Next law, or not next law, but next equation we're going to talk about is about gas density. Okay, so for gas density, this is the equation right here. Pretty simple. It's the same thing as the regular density formula, mass divided by volume. But instead we are going to be reorganizing the ideal gas law in order to find density. So if you guys remember, density is mass over volume, right? And so depending on the mass of the gas, this little U thing is mu, it's a Greek character. This stands for molar mass. Okay. So we can use molar mass to figure out the density of a gas. You all right? Okay. So this is actually just a rearrangement of the ideal gas law. If you guys are very interested in why it is the way it is, you guys can reorganize it. I'm not going to do that here. I don't want to do algebra. But yeah, well, we can just plug and chug into this equation, okay? All right, so with that being said, I'll give you guys about a minute to try 5.11. Now, one thing I do want to give you guys a heads up before I let you guys start is that the pressure is in torr and the temperature is in Celsius. So depending on what R value you want to use, you're going to have to convert those equations before you plug it into the equation. All right, so take about maybe 2 minutes to try it out. Check with the person next to you, and then we shall move on. Okay, so we convert torr to ATM and then Celsius to Kelvin. And then after that, we just need to plug it into the density formula. If you guys are interested, I did the algebraic proof for it, but it's over there for you. For pressure, again, we're going to plug in 1.053 ATM. And then we're going to find the molar mass. So what's the molar mass of radon? Yeah, 222 grams per mole. And then we're going to divide that by the gas constant. We're going to probably use 0.0821. And then we're going to multiply that by the absolute temperature, which is 373 Kelvin. And that will give us a final answer of 7.63 grams per liter. Okay. Any questions about that one? Yes.
Around that.
Yeah, if you get something similar to that, that's fine. Oh, that's perfectly fine. Yeah.
So for the equation, what's PM? Because mass of moles, the moles.
Yeah, good question. It's the mass of the gas. So however much the total sample of gas weighs, and that will be different from the molar mass and the moles of gas. Yeah. Thank you for looking at my hard work. Alrighty, so we are going to skip 5.12 and yeah, we're gonna skip 5.12 and go straight to 5.13. This is a pretty good exam question. No, this wasn't on the test. This was no workbook. Okay, but I will give you guys maybe about 3 minutes to try this out. You can split up these gases with the person sitting next to you, or the people sitting next to you. But I want you guys to find out which of these is most dense at STP and write an explanation. Now, explanations are a big part of the FRQ on the AP Chem test. But one thing I do want to tell you is please do not humanize these molecules, okay? So I know that when we talk about them, we like to say, oh, this molecule wants to react with this one. But in real life, they don't do that. They don't want to do anything. They don't have consciousness. They don't have feelings, right? And so we want to make sure that we're very precise with our language. You say, you know, this compound reacts with this compound or has an affinity for reacting with this compound because of whatever reasons. And so on your FRQs and on this problem, try not to humanize them. They don't matter. They don't have feelings. We don't care about them. Okay. They're just empty, hollow, emotionless things floating around. Just like me, exactly. I also do not have emotions. So yeah, we'll so try that out and then we'll go over it together. All right. Okay, so we have the density formula for gases up here, right? 3 different ways to write it. But let's be a little bit logical about this, okay? So if the gas is at STP, we know that it's at 1 ATM and 273 Kelvin, right? Now all of these gases are at the same temperature and pressure, right? So what that means is temperature doesn't really matter, pressure doesn't really matter, and the gas constant is the same for all ideal gases, right? So this guy doesn't matter either. So what's the only thing that matters? Molar mass. And so the greater the molar mass, the more dense the gas is going to be, okay? And so if you take a look at these 3 gases, chlorine is what, like 70 or something like that? About 70 grams per mole. CO2 is 44 grams per mole, NH3 is 17, and this guy is 28. So what is the densest gas? Yeah, Cl2. So you can say that chlorine gas is the most dense at STP. And then we can write because it has the highest molar mass. Okay, yes.
I know this one says like FC, so would it work for like so like it's the same as that?
Yeah, if they're all at the same temperature, same pressure, then yeah, that's correct.
Well, that's
Oh, they might. Yeah, not too sure. Yes. Yeah. No, that's fine. If anything, you want to keep it simple. So for when you're writing explanations, remember KISS. Keep it simple, students. But yeah, I want to keep it as simple as possible. Yeah. Yeah, that's fine. Highest. Sorry, my handwriting is very bad. Highest. Highest molar mass. Because, hey guys, I was in pharmacy school, and so I have a good excuse. It's because we all have a part of our brain that's damaged, but we can't write very legibly. No, that's a doctor. That's what a doctor does. All right. Sorry, I didn't want to say it like that, but yeah. All right. Anyway, let's move on to the next one. So we got one more gas law to look at, or actually, I think we have more than one, but we have another gas law to look at. Okay, now this gas law is called Dalton's law of partial pressures. Okay, partial pressures. And basically what this law tells us is that, let's say I have a container that contains multiple types of gases. So here we have an example right here. Let's say I have a container that has oxygen and nitrogen. The total pressure, or P tot, is going to be equal to the combined pressure of the gases inside. Okay, so if oxygen gas exerts a pressure of 159 millimeters of mercury and nitrogen is 593, then the sum of the two gas pressures is going to be the P tot. Okay. Basically, if you want to figure out what the pressure is, or yeah, what the pressure is of multiple gases in a container, it's going to be the combined pressures of the individual gases. Okay. Yes. Okay, so if we have like 10 gases in there, you just add up all their pressures and that's the total pressure. Okay, but the problems will never be that easy. Just a heads up. And I respect you guys too much to give you a question that easy. I respect you guys so much that I give you the most difficult FRQs I can find. You are so respected in this class. You are valued. You are cared for. You have a future and a hope, and so I will respect you. You have infinite value as a human being. Alrighty. Anyway, with that being said, let me show you guys how to use this in a problem. So let's look at 5.14. Now, 5.14, I'm going to draw a picture because I'm an amazing artist and I want to flex my skills. Okay. Okay. But anyway, we got a mixture of 6 grams of O2. So again, this is my incredible art skills. Okay, we got a container. And then I'm going to denote oxygen gas with red. And so we got a mixture of oxygen gas. Wow. Much art. So wow. Okay, so that's going to be oxygen gas. And then blue is going to be CH4. Okay, so we got a container that has oxygen gas and CH4. Isn't this beautiful? See that comment reflected in your grade. Okay, anyway, so inside you got 6 grams of O2 and you got 9 grams of methane. Okay, it tells us the container is 15 liters and the temperature is at 0 degrees Celsius, so 273 Kelvin. It's asking us what is the partial pressure of each gas and the total pressure inside of this container. Okay, so it's a lot of words, a lot of things, but we'll be able to solve it using what we learned. Okay, so we want to focus on the individual gases first, because if we're trying to find the P tot, we got to add up the pressure of oxygen and methane, right? So finding them individually will help us out. So let's start with O2, okay? So we are going to be looking for O2. Now, the only information that we have is that we have 6 grams of O2, or that's not the only information that we have. We also know that the volume is 15 liters, and we know that the temperature is 273 Kelvin, okay? Now, we know that we have to probably use the ideal gas law, right? So which one of these variables do we need to find in order to find the pressure of oxygen gas? Yeah, we need to find moles. And so we need to find N, and if we find N, we can plug everything into this equation, and that will give us the pressure. Now, lucky for us, we have the mass of oxygen gas, right? And so we can just set up a quick conversion. We can use the molar mass of O2, which is 32 grams per 1 mole. And that will allow us to find N. So far, so good on that one? Okay. All right, so we will get 0.188 moles of O2. All right, now that we have moles, we can plug everybody into the ideal gas law. I'm gonna rearrange it for you guys just so it's easier to plug into your calculators. And then we'll be able to find the pressure of just oxygen gas. Okay, so the pressure is going to equal our 0.188 moles. The gas constant is going to be 0.0821. The temperature is 273 Kelvin. And then we're going to divide it by 15 liters. Okay. And then if we plug all, or we calculate all that, we should get about 0.28 atmospheres. So the partial pressure of oxygen is going to be 0.28. Okay, so if you're comfortable with using this equation, I will let you guys go ahead and see if you could find the partial pressure of methane, and then see if you guys can find the total pressure after you guys do that. But do you guys have any questions before I let you guys go? None? Good. Okay. Good luck, guys. Enough of these weird hypotheticals. Let's go over the answer. So I'm not going to go through all of the calculations. I'm just going to give you the partial pressure for methane, and you should get something around 0.84 atmospheres. Okay. It's the exact same thing. The only difference is your N value will be different because obviously you have a different molar mass and a different mass. Okay, so if you want to find the p-top, you just need to add those babies up, and you should get 1.12. And that's the total pressure. All right, any questions on that? Because I'm about to make it a little bit trickier now. Of course, because I respect you all as young men and women who are capable of learning this. I respect you so much. Okay, so 5.15. So 5.15, I'll give you guys a heads up. This was an FRQ on the AP test. And this is a problem that, I don't know, these people that make these tests really like this type of problem. So I'm going to give you guys about 5 minutes to just work on this with the person next to you. And just try to figure out what's going on, see if you can interpret the problems, and then see if you guys can solve it. I highly recommend just working with somebody next to you. If you guys want to move around, I don't really care. You guys want to talk, go ahead. But try it out. And after that, we will go over every single one of those steps. All right. So good luck with that, guys. All righty, guys. Let's go over this problem. So this one is very conceptual. Okay. But let's go through it together. So it's telling us that a valve between two containers, so the valve is right here, is opened and these gases are allowed to mix. So this right here it describes the initial condition. So when they are separated, this section is 2 liters, the pressure is 1 atm, and the temperature is 273, okay? Okay. Now, this side right here, before we open it, is 3 liters, 2 atmospheres, and 273 Kelvin. Okay, so temperature is not really a big issue because it's going to be the same temperature. Oh, 298. I'm sorry. My fault. I apologize. Math is my second language. Yeah, I don't really care. I really don't. I don't need your forgiveness. I'm good. Okay. So it's asking us that when you allow the gases to mix, how does the volume occupied by N2 gas change? Okay. So if I open this valve right here, what's going to happen to the N2 gas? All the N2 was here, and then what's going to happen? It's going to slowly expand, right, and fill up the rest of the container, right? Just like a fart. You fart on one side, you open a door, it's able to go to the other side, right? It's actually almost like how a fart comes out of your body, right? There's a little opening and then it goes and it expands out. Oh, that's a perfect example. Anyway, so how does the volume occupied by N2 gas change? Okay, so you could have described that as how the N2 gas will expand to fill the container. So N2 gas expands to 5 liters to fill the container. So that will be the answer to the first part. Okay, makes sense? Because gases expand to fill the rest of the container. Okay, from there, we can figure out what is the partial pressure of N2 after mixing. Now, we're trying to find the pressure because obviously if a gas expands, it's gonna drop in pressure, right? Because it's filling up a bigger container. It takes longer for it to hit the walls of the container. And so for the second part of A, we're gonna have to do a little bit of calculation. Now, what were the two variables that changed? Pressure and volume. So we have a gas law for that, right? We got P1, V1. Oh, yeah. And then now we can plug in our values. So what was the original pressure of N2? Yeah, 1 atmosphere. Yes. And then our volume is 2 liters. I know, it was a long time ago. And then we're looking for the new pressure, which is P2. And what is the new volume for the nitrogen gas? 5. Good. Good. I know. I hate this class too. I hate chemistry. I genuinely hate chemistry. Okay, and you'll get to spread the hate with everybody. To make you guys hate chemistry as much as I do. Yeah.
So it is 0.4.
Do you get the same answer? Mm-hmm.
Liters, then I plug that in. Sorry, 5.
Oh, perfect. That's fine too. Yeah. Yeah. So if that, again, there's multiple ways to solve all these questions. As long as your calculations check out, you'll get credit on the AP test and my exams as well. So this is my way of doing it, but the new pressure of N2, partial pressure of N2 will be equal to 0.4 atmospheres. Alrighty, so based on that, you guys think you could do B and C on your own? Yeah, okay. I'll let you guys try. It's very similar. Part B is the same thing, except this time you're looking for O2. Okay, and then after that, for part C, you're looking for P-tot. So I'll give you guys maybe about 2 minutes to try that out, okay? Okay, so I'm just gonna give you guys the answers for 5.15. For part B, it's the same thing, except instead of using the values for nitrogen, you're gonna use it for oxygen, obviously. And so you will get a partial pressure of 1.2 atm. Okay. And then for P-tot, you just need to add the partial pressure of nitrogen and oxygen. You get 1.6 atm. All right. Sound good? Easy peasy. Easy. Yeah, again, I mean, the math for this is not that bad. It's just interpreting the question, figuring out like what's actually going on, what it's asking you. That's the hardest part. And don't worry if you're not super proficient at doing it yet. We're gonna do a lot more problems like this, and a month before the AP test, there will be no tests, only practice tests where we just go over problems, work on tests together, to help you guys kind of understand how to interpret these questions. Okay.
Yeah, I was like, these are the rules so fun. These are the they can be things, bro. Like actually, and there's
You have a question? Yeah, it's just long. They're long units.
You still do like what's
Yeah, for second semester, yes, I do.
these are like free tests.
Yeah, yes, they're long and they're hard. Yes. Yeah, so as the year goes on, to prep you guys for the AP Chem test, because it's a 3-hour test. Yeah, so there's gonna be days we spend the entire class period just taking the test. Yes, I need you guys to build. I need you to build that test endurance. I know you guys play sports, and you gotta be able to keep up with that long period of time. Anyway, let's move on. Okay, 5.16. So this is the reason I was setting up that thing earlier.
Oh.
But here we're gonna be looking at Okay, so this is one very common way that chemists measure gas inside of experiments and labs. And so I'm going to show you guys how it looks in just a second. But basically, what's happening here is that when you run a chemical reaction, sometimes you're going to produce a gas. And if you want to figure out how much gas you produce, right? Usually when we look at chemical equations, when we look at stoichiometry, we just weigh the solid, right? We just put it on a scale, see how much it weighs. Unfortunately, we can't put gas on a scale. We can't weigh it. And so what we have to do is instead we need to work with volume. Okay, so I'm going to have it set up right here. But hopefully you guys can see this. I have a little container, graduate cylinder. So we're going to assume that it's this tall thing right here. And it has water inside of it. And you guys see how there's markings, right? And so what happened is, okay, so what we do is, let's just say this tube is connected to something that's producing gas, right? Like a chemical reaction. So what they do is they put the tube inside the water underneath the container. This is how we capture the gas. So this is the initial volume, right? So this tells you how much gas is there originally. But if you start adding gas, you're going to see that the water level goes down, right? And so based on how much gas the chemical reaction produces, you can see the change in volume, and that will tell you how much gas is produced. So that's how we capture gas. That's how we measure gas from that producing chemical reaction. Not that cool, but I just wanted you guys to see what that looks like. Okay, that'll help you visualize the Don't try it at me, kids. I'm a trained professional. Okay, but let's take a look at 5.16 as the projector starts back up. Okay, but we have a chemical reaction, and what's happening is it's telling you that 159 milliliters of wet H2 is collected over water. So if we go back to the demo I just showed you guys, this is our little tube, and it's telling us that we collected 159 milliliters of wet H2. Now I'll talk about what wet means in just a second. What's the difference between regular H2 and wet H2? Okay, and a barometric pressure of 738 torr. So that means that the pressure in there is 738 torr. Okay, so inside of this little space where the H2 was collected, it's 738 torr. Okay, and it's asking us how many grams of zinc have been consumed. All right, now let's talk about what wet H2 is. And this is when they give you gas problems on the AP test, they love this type of example because it tests a bunch of different things at the same time. Now, if you guys take a look at this container right here, there's water underneath, right? Now, one of the properties of water is that even if it's not boiling, some of the water molecules on the surface will turn into gas. Okay, so it'll go from liquid water to gaseous water by itself. Okay, so let's represent it with blue because that's water, right? So there's some H2O molecules hanging out right here. But if you just leave water by itself, the water molecules some of them will turn into gas. And so before we even collect the H2, there's going to be some pressure of H2O. There's going to be the pressure of H2O gas in there. Does that make sense? Okay. But we also produced H2, so that means there's going to be a separate pressure from the H2 gas. And so whenever you see the term wet H2 or wet something, it's telling you it's actually the total pressure of a gas that's collected over water, because there's going to be H2 gas in here, but there's also going to be that water vapor that by itself starts vaporizing. So 738 is going to be your total pressure. Okay, it's wet because of the water vapor that automatically creates its own pressure in there. Okay, make sense? Okay, so that's why this second sentence is helpful. It tells us the vapor pressure of water at this temperature, 23, is 21.07 torr. That means that the water vapor is going to have this pressure, 21.07 torr. Okay. And using that information, we'll be able to figure out the pressure of H2. And then we can use that to figure out how many grams of zinc have been consumed. Yeah.
Know how much H2O
No, you're never gonna have to memorize it. It'll be provided for you. There's gonna be either some kind of, it's gonna be written for you like that in a sentence. There's gonna be some kind of appendix for you to look at, something like that. Yeah, good question. Any other questions? Okay, so let's try this problem out. If you think you have an idea of how to solve it, you can just ignore me and go ahead and try it out, but let's go over it together, okay? Okay, so we said that 738 is the total pressure, so let's try to figure out what the pressure of H2 is. So pretty simple. Total pressure is going to be equal to the pressure of water plus the pressure of H2, right? Okay, so we just need to plug in our value. So we got 738 torr. And if we subtract the pressure of the water vapor, that is going to give us the value of H2. Okay, so I'll give you a second to punch that into your calculators. Did I do that right? Yes. Okay, so you should get 716.93 torr. And then you can convert that into atmospheres. And if you divide it by 760, you should get 0.943 atmospheres. Okay, so that's going to be your pressure of H2. So far, so good? All right, so now that we have the pressure of just the H2, we can use our ideal gas law, PV equals nRT. And if you guys notice, we're looking for grams of zinc, right? And so if we're trying to find the grams of zinc, what we need to do is we need to find a relationship between zinc and H2. Now, if you guys remember, chemical equations are always talking in terms of moles, right? So if I want to find something about zinc, I'm going to have moles of H2. Otherwise, I don't have a way to connect them. Yeah. What whole pressure thing? Yeah, you don't need, you need this in order to find the pressure of H2. Yeah. Yeah, that's how we found the H2. We use the total pressure. Yeah, but if it doesn't ask you to find something, you don't need to go out of your way to supply that variable unless you need it in like a mid-step process. But yeah, does that answer your question? Okay, cool. All right. So we got PV equals nRT. Now we're looking for zinc, but in order to do that, we need to find out moles of H2. So what we can do is we can rearrange this equation right here into PV divided by RT. We can plug in our values for H2, and that will give us moles of H2. Any questions on why we use the ideal gas law? Make sense? Okay. Yeah, so we use the ideal gas law because if you look at the question, what we're looking for at the very end is grams of zinc right here, right? It's asking how many grams of zinc. Now, we know that in order to find grams of zinc, we're probably going to need to use this equation, right? Because we don't have any other information about zinc. Chemical equations are always talking in terms of moles, right? So this equation is saying that 1 mole of zinc, 1 mole of sulfuric acid is going to produce 1 mole of this and 1 mole of that, right? Which means in order to go from H2, which is what we're talking about right now, because we have all this information about H2 gas, we need to find the moles of H2 gas, and that way we can convert it into moles of zinc. Does that make sense? Yeah, so we're using the ideal gas law to find N, because we have pressure, we have volume, we have temperature, and that way we can find moles and then convert it to moles of zinc. All right, so if you guys plug in the values, and if you guys are doing that already, that's great. You should get 0.943 ATM. The volume is going to be right here, 159 milliliters, but if we convert to liters, it's going to be 0.159 liters divided by the R value, 0.0821. The temperature is 23 degrees Celsius, so we got to convert that, so 296 Kelvin. And then that will give us a total of 0.00617 moles of H2. Right here. Yeah, make sure if you guys have any questions, you let me know because hint, one of these might be on your exam. One or more.
Can you make this test? No, like I was saying, like more.
Oh,
That's like that's a death.
No, I you know what I'm
watch me make it one question and like stupid long. Yeah,
saying?
Yeah.
yeah.
And they're all written together.
I love those tests. So easy to grade. It's so easy to grade.
Or no, it's like and if you get A wrong, then you're like guaranteed.
Exactly. I love those tests. All right. Anyway, so we got 0.00617 moles of H2. If you look at the relationship, what's the ratio between H2 and zinc? Yeah, 1-to-1. So we can automatically say, hey, this is going to be 0.00617 moles of zinc. And then we got to finish it up by converting it to grams from there. Pretty simple process, just molar mass. So you just need to divide or multiply by the molar mass, which is 65.4. And so you should get a final answer of about 0.403 grams of zinc, something along those lines. If you got like 0.39, 0.41, that's totally fine. Alrighty, any questions? Easy peasy? All right, cool. We'll take a quick break right now. So if you guys want, you guys can go to the restroom. If you want me to light your hand on fire, we could do that. Yeah, we'll all do that. Okay, but we'll take a quick